Hello everyone, welcome to Chem Analysis. Today I will solve previous year CSIR-NET December 2019 Inorganic Chemistry 2-marker question. If you are new in this channel, then please subscribe to my channel, and you can also share this video if you found it useful. So let's start this discussion. The first question is asked from coordination chemistry, and you have to tell about the order of molar extinction coefficient for this different coordination complex. In coordination complexes, you will see that some of the coordination complex solution will show a color, and it is mainly due to electronic transition in the visible region. Now, higher the possibility or higher the intensity of this electronic transition, higher will be the molar extinction coefficient for that complex. Now, among the given complexes, if you see in chlorophyll, is an organometallic complex where a metal center, that is magnesium 2 plus, is present at the cavity of a macrocyclic ligand, that is porphyrin ring, and the color of the chlorophyll generally arises due to pi star electronic transition in the ligand, that is the electronic transition from HOMO of the porphyrin ring to its LUMO. Therefore, the intensity for electronic transition for chlorophyll will be highest among the different coordination complexes. Now, next, if you see that NiCl4 is a tetrahedral complex. Due to DP mixing in tetrahedral complexes, the electronic transition was allowed, that is Laporte allowed. In nickel Cl4 2-, nickel is in +2 oxidation state, that means it is D8 complex, and the electronic configuration will be E4 T24. Therefore, here electronic transition will be Laporte allowed due to DP mixing. But in octahedral complex, there is no possibility of DP mixing. So, molar extinction coefficient for octahedral complexes will be lesser than that of tetrahedral complexes. Now, between these two octahedral complexes, in chromium 2 plus, that is D4 system, and electronic configuration will be T2G3 Eg1. It is T2G and it is Eg. T2G3 Eg1. The electronic transition will be spin allowed but Laporte forbidden, and in tetrahedral complex it will be both spin allowed and Laporte allowed. So, in case of tetrahedral complex, electronic transition will be more intense and molar extinction coefficient will be higher than that of octahedral complex. Now, there is another complex, that is MnH2O6 2 plus. It is D5 system, that is T2G3 Eg2, and it is both Laporte forbidden and spin forbidden. So, the molar extinction coefficient for manganese H2O6 2 plus will be least among the given complexes. Now, if you want to know that what is Laporte allowed, what is Laporte forbidden, Laporte allowed transition will be when delta L is equal to ±1. Now, in case of octahedral complex, since there is no DP mixing, the electronic transition is from D to D. Therefore, delta L will be 0 and Laporte forbidden. But in case of tetrahedral complex, due to DP mixing, the electronic transition occurs from D to P. Therefore, delta L will be ±1. So, we can see that molar extinction coefficient order will be this one. Chlorophyll will be highest, then NiCl4 2-, then chromium H2O6 2 plus, and the least molar extinction coefficient will be for manganese H2O6 2 plus. In the next question, you can see that you have to tell about the number of CO stretching bands in IR spectra of facial MOPPH3 CO 3 and trans MOPPH3 CO 4. First of all, we have to draw the structure of these two given complex. In the first case, it is facial MA3B3 type complex. Therefore, since it is facial, 3A will be cis to each other, that is if we consider PPH3 as A, So it will be this one, since both the PPH3 3 PPHC ligands are cis, and similarly 3 carbonyl ligands will be also cis. Now we have to find out the point group, and for that you have to see the number of symmetry elements present in this complex. You can see there will be one sigma V plane containing this PPH3 ligand, this molybdenum center and this carbonyl center, and will cut this molecule into two equal halves. Therefore this CO and this CO will be similar, and these two CO group will be different to this one. Okay, therefore you can see in this complex there will be two CO stretching bands. Since these two CO group will be similar and this will be different from these two one, so there will be two CO stretching bands. In case of trans MO-PPH3 hold to CO4, two PPHC ligand will be trans to each other. I have solved such type of questions in my previous video. If you want to watch that video, I will give the link in the description box. You can watch that video also. There I have solved more questions regarding such type of problem. Here you can see that there will be one C4 axis and there will be two sigma V plane. One will bisect this molecule into two equal halves. Therefore this CO will be similar and this two CO will be equivalent, and similarly there will be another sigma V plane that will bisect this molecule along this direction containing this that will pass containing this PPHC ligand, molybdenum center and this PPHC ligand, that will convert CO and this CO equivalent, and similarly this CO and this CO equivalent. Therefore we can see that all the four carbonyl ligand are equivalent, and as a result there will be one CO band. Thus we can see that the first complex will show two CO bands, stretching bands, and the second complex will show one CO stretching bands. Is it okay? Now this question was asked from lanthanide elements, and here you have to tell about the pair for which there is a significant deviation between the experimental magnetic moments and calculated magnetic moments. That is calculated from this equation: mu effective is equal to G into mu effective is equal to G into root over J into J plus 1. Such formula is applicable for lanthanide elements for calculation of effective magnetic moments, but for F0, F7 and F14 elements such equation converts to that of transition metal elements, that is spin only. Okay, since J is equal to L plus S, and in case of F0, F7 or F14 L is equal to 0, so J converts to S and the equation becomes mu spin only, that is mu spin only or mu effective is equal to G into root over S into S plus 1. So for F0, F7 and F14 there will be no difference between the experimental values and calculated magnetic moments. So the first option, since gadolinium 3 plus is F17 and lutetium 3 plus is F14, there will be no difference in the calculated and experimental magnetic moments. Now keep in mind one thing, that for such type of questions, when you are asked that there is a difference between the experimental and calculated magnetic moments, the answer will be samarium 3 plus and europium 3 plus. You will observe that only for these two lanthanum elements in +3 oxidation state, due to filling of the higher J level, due to increase in the population of the higher J level at room temperature, this filling of the higher J level, that is electronic population at the higher J level increases, and that occurs at room temperature, and therefore in such cases when you try to calculate the mu effective value using this formula, since here J value increases, therefore you will observe that the mu observed or experimental value for these two lanthanum 3 plus ion, that is samarium 3 plus and europium 3 plus, is greater than that of mu calculated value only for these two lanthanum plus 3 element. Okay, therefore option number 4 will be the correct answer, and there will be large deviation between the experimental and calculated value for these two lanthanum 3 plus element. In the next question, this is a new type of questions. It is asked that in common glass electrode, alkaline error that causes at pH is greater than 10 is least for which solution? In generally, in case of glass electrode, there occurs two type of error, that is, one is acid error that occurs when pH is near about 1 to 2, and another is alkaline error that occurs when pH is equal to 10 to 11 or 9 to 11. Okay. Now, in case of alkaline error, due to presence of alkali metal cation, they move in the electrolyte solution and therefore they reduces the transport number of H plus ion that is present in the solution and for which the pH arises, and there due to decrement of the transport number of the H plus ion, there is observed some error in the calculation of conductivity. There is a decrease in the calculation of conductivity due to involvement of this alkali metal cation. Now, the lesser will be the mobility of the alkali metal cation, lesser will be the alkaline error. Lesser mobility of the alkali metal cation, lesser will be the decrement of the transport number of the H plus ion, and lesser will be the decrement of the conductivity. Therefore, lesser will be the alkaline error. Now, among the given alkali metal cation, K plus has the largest size, therefore it will have the least mobility, and for KCl solution there will be least alkaline error. Therefore, option number 4 will be the correct answer. Is it okay? In this question, it is asked that for an octahedral copper 2 plus complex which shows axial EPR spectrum for which G parallel is greater than G perpendicular, you have to tell about the geometry of copper 2 plus complex and the orbital containing the unpaired electron. Copper 2 plus is a D9 system and it is a tetragonally distorted complex, and the electronic configuration of D9 copper 2 plus will be like this. Now, how the T2G orbital will be splitted or EG orbital will be splitted depends on the G parameter. If you want to know more about the G parallel or G perpendicular thing, you can watch my previous video where I have solved few previous year questions on EPR spectroscopy. You will get detailed knowledge on G parallel and G perpendicular from that video. That G parallel mainly indicates that electron density along Z axis is higher than that of perpendicular, that means XY plane. Okay. Therefore, along Z axis, that is dz square or dxz, in case of T2G dxz and dyz will be electronically rich, and in EG orbital dz square will be electronically rich. Therefore, in dz square orbital there will be 2 electron and the unpaired electron goes to dx square minus y square orbital. Since in EG there is dz square and dx square minus y square, so the orbital will be splitted like this. Here will be dz square that will contain the paired electron, and here will be dx square minus y square that will contain the unpaired electron. Similarly, the T2G orbital will be splitted like this. That is, here will be dxz and dyz, and the higher orbital will be, higher energy orbital will be dxy. Therefore, we can say since d z square orbital contains more electron density. Repulsion between the metal electron density and the ligand along the z axis will be higher, and therefore the complex will be tetragonally elongated, since the repulsion along the z axis between the ligand and the d electron density of the metal center, that is d orbital, d z square orbital of the metal center is higher than that of interaction between the ligand and orbital along xy plane, that is dx square minus y square. So it will be tetragonally elongated and the unpaired electron resides in the dx square minus y square orbital. Here this is a very simple question. You have to tell about the common hapticity observed for coordination of C60, that is fullerene, to a metal center. Generally C60 shows hapticity of 2 while coordinating to a metal center. Hapticity for C60 is equal to 2. It binds through a pi bond. Therefore hapticity is 2. This is a very basic level question. Here it is asked, we have to tell about the order of bond angle for gaseous NF3, SbF3 and SbCl3. So as we know, when you go from in group 15 element, when we go from top to bottom, that is nitrogen, phosphorus, arsenic, antimony, the size of the element increases. Size increases and electronegativity decreases. Okay. Now with increase in size, the bond length, that is the central atom and the halogen bond length increases. Therefore as we go from nitrogen to antimony, the central atom and halogen bond length increases. On the other hand, with decrease in electronegativity of the central atom, the electron density of the central atom and halogen atom shifted towards the halogen atom due to decrease in electronegativity of the central atom, and as a result the bond pair repulsion decreases as we go from nitrogen to antimony. Now if we compare between NF3 and SbF3, the bond angle in SbF3 will be lower than that of NF3. Now between SbF3 and SbCl3, if we compare the bond angle, since fluorine is more electronegative than chlorine, so the bonding electron density will be shifted more towards fluorine atom in SbF3. Therefore bond pair repulsion will be least in SbF3, and as a result SbF3 will have least bond angle. So after that it will be SbCl3 and the least bond angle will be SbF3. So this will be the order, and we can see that option number 4 is the correct answer. This is a very easy question. You have to tell about the most stable vanadium species in aqueous medium. Now most stable vanadium species in aqueous medium where vanadium exists in +4 oxidation state. Now in the given complexes you will see that only in case of 2 vanadium is in +4 oxidation state, and such complexes are such vanadium 4 complexes or vanadium 4 ion known as vanadyl complex, and this is the most stable complex of vanadium in aqueous solution. Here in the given non-fluxional complex you have to tell about the number of resonances in the 31p NMR, where since within bracket there is 1 is, that means proton decouple 31 phosphorus NMR, and for phosphorus I is equal to half it is given. Now in this case you can see that this phosphorus is 2 bond apart from this phosphorus, and since 2J PP coupling is allowed, so this phosphorus atom will be coupled or splitted will be coupled with this phosphorus atoms and will be splitted in the NMR spectrum. And since there is one phosphorus atom, this phosphorus, if we number it A and it is B, then PA, for PA there will be 2 NiPb plus 1. There will be such number of lines in the spectrum, and this will show one resonance that will be that is for PA there will be doublet, and for PB that will be also splitted by PA similarly, and it will show also double line, that means doublet. Therefore in this complex, in the 31P proton decoupled NMR, there will be two doublets. This is a question asked from atomic structure. You have to tell about the products observed when K electron was captured by nucleus. When a K electron is captured, that means electron E minus is captured by the nucleus, a proton, that is H11, gets converted to a neutron, and along with that, since proton is converting to neutron, there will be elimination of a particle, that is neutrino. Okay, therefore when K electron capture, it is K electron, when K electron captures by nucleus, one proton get converted to neutron and another particle is eliminated, that is neutrino. And when neutron gets converted to proton, there will be elimination of another particle, that is known as antineutrino. You can remember it that when proton converts to neutron, along with that neutrino eliminated. When neutron converted to proton, antineutrino eliminated. Okay, it is symbolized as like this, and antineutrino is symbolized by bar on the neutrino. Therefore here will be neutron will be eliminated and along with neutrino. Therefore A and B will be correct answer. Second option is correct. This is the last question for this discussion. You have to tell about the correct statements for oxymyoglobin and cytochrome P450, that is in resting state. Now in both the cases, there is the central metal center is iron and it is attached to protoporphyrin dianion. That means first option is correct, and in the second option it is given that the fifth ligand bonded to the metal center is same for both the complexes. It is not correct, since in case of oxymyoglobin, the ligand attached to the fifth coordination center is histidine. That is nitrogen center of histidine is attached at the fifth coordination center, and in the sixth coordination center there is oxygen. It is for oxymyoglobin, and for cytochrome P450, fifth coordination site is filled up by cysteine ligand of the protein chain, and it is coordinated through the sulfur center with the central iron center. Therefore both the fifth ligand in oxymyoglobin and cytochrome P450 is not similar. They contain single active site. It is okay for both the two cases, since here is one active center, and in case of cytochrome P450 there is also one active center, and they contain metal ion in +3 oxygen state, and it is in case of oxymyoglobin, iron center is in +3 oxygen state and oxygen is in superoxide form. Similarly in case of cytochrome P450, the central metal center iron is in +3 oxygen state and oxygen is in superoxide form. So this is also correct for both the two cases. Therefore we can see that option number A, C and D are correct. So this is the correct response. So that's all for this discussion. If you like this video, you can also share it with your friends so that they can also learn something new. And if you are new in this channel, then please subscribe to my channel. Thank you.